Hello. My project of wireless communication is about fast pairing of device-to-device link underlay for spectrum sharing with cellular users. And my name is Zixiang Nie. And here is the overview of this demo. And this project is based on this paper, fast pairing of device-to-device link underlay for spectrum sharing with cellular users. And I'm going to cover this content in the demo. So first, the T2d communication. Let me give a brief introduction. So T2d communication is defined as a direct communication between two mobile devices, and their communication they're not going to traveling over the base station and core network. So currently in traditional cellular network, even A and B want to talk to each other and they are in the coverage of the same cell, they still need to forward the packet up to the core network and forward down to the 2B. So usually the D2D communication need the base station to enable it, and they bring some um, merit for the cellular network. They can increase the spectrum efficiency and energy efficiency and improve the latency and even can extend the coverage of the network. And SendGPP protocol specification release 10 and known as LTE Advanced, they have include this kind of communication for proximity services. And I got this figure from this paper. This gives us a brief uh, using scenario of D2D communication like content distribution, M2M, relay, and cellular load offloading, and face-to-face gaming like that. So there are four categories of D2D communication. They are classified by how to use the spectrum resources. So if they are using cellular spectrums, they will be called in-band D2D. So if they share the cellular resources of the cellular users, they will be the underlay. And if they have dedicated cellular resources, they will call the overlay. And other researchers, they propose the outband D2D communication. They use instead of cellular resource, they use some other unlicensed spectrum like Wi-Fi or Bluetooth. So this paper narrowed their scope of research in-band and related D communication. So in this kind of communication, they share the D2D links share the cellular spectrum, so it will introduce the co-channel interference to either of them. So the increased interference will reduce the throughput of normal cellular user communication. So here we need the link budget um, because that is why the D2D communication need to be enabled by the base station. So the well-considered algorithm of enabling D2D communication could increase the overall sum rate of the cell, and also direct communication between users to save energy. They don't need to talk to the base station that is really far. And also in some special scenario like face-to-face gaming, face-to-face file transfer, they can improve the latency. And also in some extreme scenario like some users have good signal, they can share their bandwidth with those have bad signal. The signal strength, the received signal strength will vary by devices, so it can enhance the cellular coverage. So this is the main problem the co-channel interference doing to handle in this in-band underlay D2D communication. So here is how this paper proposed their research under this kind of scenario. So first they have a cell, and in the center of the cell they have a base station, and in the cell they have N cellular users and M D2D links. And each pair of D2D links, they have done the association between them, and they are going to create the D2D communication, and they ask the base station to enable them and allocate a um, cellular resource for them. And so the base station is going to find the most optimal matching of the whole resource sharing, and they only consider the uplink for either cellular users and D2D users. So how the base station make this maximal matching decision? Here the paper they propose a algorithm and it contains two steps. The first step they need to build the D2D link candidate list. It is from the cellular user's perspective. They found those D2D links with interference under the threshold. Um, so here they use the SINR as the threshold here. So the signal is here is the received signal from each COE, each cellular user from the base station. And interference is from D2D transmitter to the base station. And the noise here is the background noise. Here in their implementation, they consider the large-scale path loss. And in my implementation, because they are not giving too much detail about how they calculate the path loss, so I use this log normal distribution to describe the path loss, just like provided in the lecture 4. I use this equation. Here, d is the distance between the cellular user and base station, and n here is the path loss exponent. I use 3.5, a typical value of urban cellular scenario, and here x is describing the shadowing, and so I also need the free space propagation model to calculate this unit path loss. Use this equation. So after I get the path loss, I can get the receive power from the transmit power divided by decimal version of path loss. So here, after from the cellular perspective, they got a list. So the next step from the D2D links perspective, they are going to further narrow the list. They filter out those have too large interference to D2D receiver, and also they use the SNR threshold. So here the signal is received signal from D2D transmitter to D2D receiver, and the interference here becomes the cellular transmitter to D2D receiver and annoys you the background noise. So after this step, we've got the all possible pairings of the between cellular users and D2D links. So step 2, we need to find the optimal matching in terms of sum rate. So intuitively, the best way to do this is calculate every possible matching and choose the one that with the most sum rate. But it seems consumes really a lot of time to do that. It's not fit the mobile scenario. So the paper proposed their algorithm called inverse popularity pairing order. In this method, they remember the match, every match the base station have made, and they pair the cellular users to the least popular D2D link. So also after that, they optimize the transmission power to achieve the optimal sum rate of cellular to base station and D2D link. So here they think their algorithm can balance the computing time and fairness of D2D links. So here in my experiment, I did two set of experiments. The first one is the overall sum rate versus number of cellular users. I have fixed transmission power of the transmitter I. So here we can see that the sum rate increases as the number of cellular user increases. Well, that's normal. And the sum rate increases as the transmit power of cellular user becomes higher. So we can see that with 500 milliwatt, the sum rate is higher than those with 250 milliwatt. And also the sum rate increases as there are more DC links. This is look at here, and this is not pretty obvious but we can get the numerical result from the table here. Actually, they have a little increases in sum rate. So with D2D sum rate, with D2D communication enabled in the cellular network, the overall sum rate becomes higher. And here is the second set of the experiment. It is the sum rate versus the sum rate of D2D pairs versus the number of D2D links. So here I have the fixed number of cellular users and fixed transmission power of the cellular users, and the sum rate increases as there are more D2D links, except for this 25. And the sum rate increases as the transmit power of the D2 link becomes higher. So this with 200 milliwatt, they have higher sum rate than this 125 milliwatt. So here I'm going to show how my code is working with it. My code is not like one click and get everything. I need to keep changing this transmit power and the numbers of cellular user and D2D users as I do the experiment. So let's run this. This is the transmit power of cellular users is 250 milliwatt, and transmit power D2D transmitter is 125, and we have 140 cellular users and 25 pairs of D2D users. And I run it for 1,000 times and get the average sum rate. Yeah, here is the result. The sum rate is 327 bits per hertz, and here I got the matching metric indicating every matches in this specific scenario. So each row represent a D2D link, and each column represent a cellular user. So here we can see that cellular user 42 it shares its upload resources to this D2D link 12. So here is the conclusion. Um, Here is the conclusion. So first, the algorithm in the paper, they could find a matching that increased the overall sum rate. As we can see that with T2D enable, the sum rate increases. And also the introduce of D2D communication, they can help with the spectrum efficiency in the cellular network. And also from there are more D2D links and once more overall sum rate of the cellular network. So here is my demo for wireless communication project, and thank you.